Hi everyone. Today we are going to start designing one of your combinational circuit, especially your adder. So already we have seen your basic adder circuits like half adder, full adder, and your subtractor circuits also like half subtractor, full subtractors. But there is a circuit which usually you will face in your exams, like design or explain the operation or the working principle of 4-bit parallel bar adder subtractor. Got it? So you need to design a common circuit which will perform both addition and subtraction operation. Usually as a budding engineer they will ask you to design for 4-bit addition and 4-bit subtraction. So that we are going to see, and also along with that what is the fast adder used. So what is the disadvantage in the existing these kinds of half adder, full adders, and half subtractor and full subtractors. Okay, so why they move to a fast adder? Okay, how to design a fast adder, how to design a 4-bit parallel adder subtractor. So for that you should know what is a 4-bit adder, parallel adder, and what is a 4-bit subtractor separately. Okay, so we will see all the four circuits today in today's session. So far we have completed all these things. So today we are going to complete the carry low head adder. So in your classrooms, I've completed decoder, encoder, priority encoder. So as a recap, just go through the design procedure of any combination circuit. Always you'll be provided with a problem statement. From that you have to identify the number of inputs, outputs, and from that you have to sketch a block diagram. And you have to name the input output variables. And thereafter, you would be plotting your truth table with a possible combination of inputs and output values. And from that, to get a simplified expression, you will map a Karnaugh mapping method. That is to simplify. There are three methods. You can go for either laws and rules or the theorems, or you can go for a Karnaugh mapping method or tabulation method. Always we prefer, if it's less than 5 variable now, we prefer K-map. So we go for K-map. From that you will obtain a simple logic circuit, simplified logic expression. From the logic expression you have to plot your logic circuit. Okay, so this is how the design procedure goes on. So next, since I have recorded already, in that live video audio is not captured, so I'm recording this again. So you have the some examples written already. So with that itself I will teach you. So this is a simple 4-bit parallel adder circuit which you will find when you Google. This is a Google image I've taken. Okay, so if you see, if you want to add a 4 bits of two input information, two input information is what, A and B. I have to add two things which is of how many bits, 4 bits. Say suppose if I want to perform 11 plus 14 now, how exactly the circuit will operate now? It will just operate on the binary value. So the decimal to the conversion happens. Okay, and you have the binaries to be fed. So what is the binary value of A right now, which is of 4 bits, 1011, B 1110. So when you try to add these two combination of inputs, for the first stage of addition, what is happening? You are adding 2 bits. 2 bits, to add 2 bits, any 2 bits, half adder is enough. So 1 plus 0 is 1. So it is producing a sum, no carry is being generated. Okay. So initial carry we call it as a C0. Next carry, if it's generated, we call it as a C1. So similarly as like for others also. Next is what? Next is a bit of addition is what? 1 plus 1. 1 plus 1 and previous carry was not generated, so 0. So 1 plus 1 is what? 10. So 0, sum is 0, carry is 1. Here carry got generated from this stage and it got propagated to the third bit of addition. So now for all these things, for the next consecutive stages of addition, you are performing, you will or you may or you may not be performing the 3 bits addition. So to perform the 3 bit addition, you need a full adder. So how many ever bits you are going to add for any two input signal, those many full adders in general people will choose. So if they ask you to design and explain a 4-bit parallel adder, this is a block diagram, because one full adder will have one XOR and one XOR and three minimum three gates of AND gates. Okay, so you can't draw the full. Instead, you are drawing a block diagram of it. Okay, but the inputs are has to be denoted. So initially you will foresee in initially there is no carry for a full adder. So the third bit is made 0. Whereas the next consecutive stages you will not mention, because you may or you may not be propagated with a carry. Okay. If this generates a carry, this C1 will have a carry to be propagated like that. Okay. So this is a general block diagram, and likewise you have to take an example. You have to add and show. Okay. You have to explain the circuit, which is a very simple circuit. So I'm moving to the 4-bit parallel subtractor. Subtraction, if you want to perform now, actually you'll be thinking you have to take a full subtractor 4. That is also good, but always we people now, as of now, performing even the subtraction using a adder circuit. So if you want the same adder circuit to perform a subtraction now, it is always recommended to go for the taking the complements of the subtrahend. What is the way of, there are so many ways: one's complement subtraction, two's complement, nine's complement, and so on. Whereas always we prefer two's complement subtraction. In two's complement subtraction, the second input which you want to subtract, or we call it as a subtrahend, this you call it as minimum. So the subtrahend has to be taken the two's complement. What is two's complement? So suppose, for example, I've taken this 100. So the two's complement of it is what? First one's complement 0, 1, 1, 1, and add 1. So what is the two's complement? 1, 0, 0, 0. So this value should be added with this. Exactly this is what would be happening if you choose a adder circuit to perform a 4-bit parallel subtraction. So this is a 4-bit parallel subtractor block diagram. Here only two things has to be modified. What is that? I need the circuit to perform two's complement in addition. Two's complement is done first using an inversion operation, and then we are added a 1 or the high input signal at the LSB bit, that is the initial stage. So you have to force C0 is equal to 1 initially, and then you will be providing the other inputs bits, and for the second always the B input signal will be complemented and it will be provided to the adder circuit. So in this stage itself you will be completing your ones complement, and after processing your ones complement, it will be provided along with the A input signal to all the adders simultaneously. And also already your C0 initial input will be C0 is equal to 1. So ones complement 1 plus 1 will be done. So altogether I could say that a 2's complement will be done already. So even if you try to perform a subtraction operation for these two set of input signal, it will be performing an addition operation, but for that to perform a already this, what is that, it has to satisfy the condition of 2's complement. So that would be provided with the help of what? By infusing your inverter over all your subtrahend bits, and infusing your or making or forcing your carry, initial stage of carry, to be 1. So only changes initial carry to be 1, and all your B bits, B input signal bits has to be complemented. To take complemented, inverter is enough. Okay. So this is how you will draw with an example. You will explain your 4-bit parallel subtractor. So these are two different circuits to perform two different operations. Say suppose if you want to perform the same circuit, both the operation at the same not simultaneously, but one user can perform addition and see, and they may go off, and the same circuit could be used to perform subtraction also at a time. Okay, same circuit, but how one can make use of it for addition purpose, and other one could make use of it for subtraction purpose at a time. So This is a modification they have done. What is that now? Instead of having a NOT gate, you just replace with XOR. Why now? And XOR na, it is a two input signal. Two input signal na, one input signal is sacrificed for carrying the actual B input signals, B input bits information. Okay, like the 0, 0, 1, 1, 0, and what is A? 0, 0, 0, 1. They'll be carrying till this stage. Whereas the other input signal of your XOR is all are tapped together, and even the first control signal C in the carry, initial carry is also tapped to the same wire, and they are calling it as a K, control signal. In some of the books you could see it as a AM, so which is a control signal. If K is equal to 0, what happens? That means K is equal to 0 na, C in 0. C in 0 na, it's mostly probably looking like your parallel adder, right? When Cn is equal to 0, it will perform addition operation. How? Because one of your input to your XOR, what is your XOR truth table? When you have different inputs, your output is high. Okay, so now I'm dividing the truth table of XOR. Observe that when one of the input signal of your A is 0, whatever is B is 0 na, output is 0, 1 na 1. That is the XOR output. So it is carry. So when K is equal to 0, whatever the B bits of information you're providing, it is just acting as a buffer. So for an XOR, if one of your bit is 0 now always, it will act as a buffer. When one of your bit is high now, it will act as a inverter. Look at that. When one of your signal is always forced to 1, if the other input is 0, the output is 1, and 1 and a 0. So it is inverting. So here I want to perform both the operation. If you want to perform addition, give the control signal as 0. So Cn 0, it will send the signal as such. And addition operation will be performed by adder circuits. If it's 1 the initial carry will be forced to 1, and one of your inputs of your, that is your B inputs, will be complemented simultaneously, and next operation will be addition will be made, so that here 2's complement is over. Since because here inversion is over to your second bit, after inversion you are adding with the 1, and thereafter with the A, and it is the value of the carry will be getting propagated. So if you want a common circuit which will be performing addition and subtraction at a time, you can go and replace NOT gate by a XOR. That's all. So when XOR, one of your input is 0, it will act as a buffer and will perform the addition operation. And when one of your input signal is 1, it will perform complement, that is inversion operation, to your subtrahend bit, that is your B bit, and 1 will be added simultaneously. So finally you will obtain a 2's complement for the B signal, B bits, and finally it will be added with A. So when K is 1, it will perform inversion operation, and it will act as, it will make the circuit to function as a subtractor. Okay, so this is like this you have to explain in your theory with whatever the explanation I have given. Okay, so this is a simple explanation for 4-bit parallel adder subtractor. And these though we have these many circuits individually to perform adder subtractor, and also we have a common circuit, but still we prefer a carry lookup adder. Why not? That they call it as a fast adder. Why not? Here look at that each stage, this will be a valid output only when the carry is getting propagated from this stage to this stage. Likewise to all the, so the final, the next stage of addition will, it has to depend on the preceding stage of carry. So one full adder has at least 3 different gates which will take its own time, at least say suppose 30 nanoseconds. Now imagine how many stages of additions you will have, and for those many times it has to wait to propagate and produce the output final sum and carry. So they thought, why can't we predict, depending on the input combination, as soon as we receive, we can predict the carry, what the carry could, whether the carry will generate or not, it will propagate or not, all those could be done. So how? So based on that, we can design a circuit. People thought and they designed and they came out successfully with a carry lookup adder, which we call it as a fast adder. So this is your fast adder. See, I am making use of the past slide. So that is why you will have these script links. So this is a fast adder, which we call it as a carry lookup adder block diagram, which involves the full adder circuit. And separately you have something called 4-bit carry lookup adder, which will predict and say whether a carry is going to be generated or not. So how that would be, how that is possible to predict, like why? Take the, say so for example, full adder truth table. Observe that I can divide this full adder circuit into 3 cases. For the first 2 cases, when both the inputs A and B are 0, even if carry is previous carry, the Cin is what the previous carry, even if its carry is generated or not, here generated and this is not generated, the carry output, the final carry is not generated. So for which case? For these 2 cases. So this we call it as a no carry generated condition, and we will denote with a notation called C out is equal to 0. Okay, the final carry out is 0. And here the next 4 cases, look at the 4 cases of inputs. Whenever A is 0, B is 1, whatever the carry generated previously, that is getting propagated to the next stage. 0 na 0, 1 na 1. Also it is same for when A is 1, B is 0, whatever the previous carry, 0 na 0, 1 na 1. So these four conditions with these 2 cases, like when A is equal to 0, B is equal to 1, and A is equal to 1, B is equal to 0, I call this as a case called carry propagation. Carry is getting propagated, previous carry is getting propagated out. So C out is equal to C in, generally speaking. And the last 2 cases, look at the last 2 cases, when both the inputs are high, irrespective of your previous carry, whether carry generated or not, your final carry is getting generated. So for carry is surely getting generated for these set of inputs. Okay, so C out is equal to 1. Even if it's like a 3-bit addition, even if it's the previous carry 0 or 1, your carry will be generated. So that is what they are trying to say. So now I'm going to write the, so we are not worried about no carry generated. Okay, so when and all carry is getting, so we are predicting about the carry, internal carry C0, C1, C2, C3. So we need an expression and circuit for that to predict. So generally when and all carry is getting generated or propagated at only in these conditions. These 6, that is 1, 2, 3, 4, 5, 6, 7, 7 conditions. Okay, so we are going to write that in terms of expression, since already we have splitted these into 2 cases, carry propagation and carry generation. So always C is equal to what? G plus Pi. What is G? Carry, either carry would be generated by those cases or carry would be propagated from the previous. So those 2 expressions, look at the expressions. When and all carry getting propagated whenever A is 0 and B is 1, or A is 1, B is 0. So simply speaking, it looks like A B bar plus A bar B, so we replace with XOR gate. Irrespective of Cn, whether it's Cn, whatever Cn, it is getting propagated. So whatever is Cn, for these 2 conditions, whatever Cn, it is getting propagated. So Pi, so what is Pi getting propagated now? The previous carry. So while writing the final expression, we will write it as Pi Ci. Okay, Ci minus 1. When and all carry is getting generated? When A and both are high. So simply you can write it as AI, BI. When both are, that is A and B is high. Okay, simply you can write it like this. Or if you write the expression A, B, C in bar plus A, B, C in, take out the common term A, B, C in plus C in bar. C in plus C in bar is 1. So you will have AB. So carry is getting generated, carry is getting propagated. So these are the two expressions. So altogether, what is all about carry? No, is when and all carry is getting, we are dealing with carry. No? When a carry is generated or carry is propagated, when the previous carry is getting propagated. So you call it as C naught. Say for the first initial stage of carry, C naught is equal to G naught plus P naught into C in, that is initial carry. C1 is what? G1 plus P1 C naught. So these are the suffixes are nothing but your stages of addition. Okay, so that is how in your books you will see, because in many of the books straight away from the full adder circuit they have given the expressions which you won't understand. So a carry could be predicted just from the two cases, whether it is getting generated at that stage of addition or carry is getting propagated from the previous stage of addition. Okay, and some you can write the expression as you all know, P naught XOR C naught, P1 XOR C1. Okay, so specifically speaking, what is C naught, C1, C2, C3? How it came, na? This is how. From the truth table. General expression we have derived, no? That you have to write it. So what is the C1 stage of now? It is nothing but your, actually speaking, C1 should be, this is the correct expression. This I have taken from a Google picture, which is wrong. C naught is equal to G naught plus P naught Cn, and C1 is equal to G1 plus P1 C naught. And for the third stage of addition, uh, the third bit of addition, which we call it as a here 2, suffix with a 2. So C2 is equal to, carry would be generated at that while adding those two bits, or it would be propagated from the previous carry. Previous carry is what? This is full expression. If you substitute here and multiply, you can get the expression like this fully. Okay, so simply you can denote with a block 4-bit lookup carry lookup adder circuit, and with the inputs what is the carry look ahead now? You're predicting, you're foreseeing it all. That's all. Simply speaking, you're trying to foresee whether a carry would be generated or not. So what are the cases would be contributing now? Either through propagation or generation process, a carry would be generated. A carry would be contributed. Okay. So for propagation, XOR, generation and operation. So that is how many ever bits you are dealing with, those many gates. And finally, how the sum is getting propagated, you know all your P naught that we have given. So P naught XOR C naught. Okay, so simply you can draw like this and you can complete. I hope you would have understood. And also I have brought expression. This is how the expressions would be there in your books. So how they came out now, this is how, from the truth table. Okay, for say suppose if it's a general n stages of addition, you have to denote with n. Okay, if it's 4 or specifically they are asking, you have to specify and resolve the cases assuming I is equal to 0, 1, 2, 3 and 4. So this is the final. Using combination circuit, instead of simply putting a box like that and writing 4-bit carry lookup adder, you can also specifically draw, because you have the expressions for C3, C2, C1. Those expressions using combinational circuit you can draw it. Okay, I hope you would have understood. Thank you.